Hello, everyone. Thank you for joining us here this first webinar where we'll have Raven give a talk on his nnAudio tool. It's great to see that we have a lot of folks joining, I think some from Europe, some in Asia. Maybe I'll briefly introduce Raven, and when he gives his talk, you can note down some questions in the chat or raise your hand, and we can have questions, more detailed questions at the end. So Raven is a PhD student at SUTD. He did his bachelor's and undergrad at the University of Hong Kong and has since been working on using triplet neural networks for speaker identification, for emotion classification based on music. And now he's mostly working on audio transcription, for which he built this very cool library, nnAudio, as he'll explain, which does very cool GPU processing for spectrogram extraction. Raven, if you're ready, then I'll leave it to you.
Hi everyone, I'm Cheuk. My English name is Raven. Today I'm going to present a library called nnAudio. It is a GPU audio processing tool. There's a QR code on this page. If you're interested, you can scan the QR code to access my GitHub, and you can download nnAudio there. Let's get started. So why do we need to extract spectrograms? The problem is if we use the raw audio to feed to our model, it is quite difficult to extract information directly from the raw audio. So most of the time we convert our audio recordings into spectrograms. And then we have a data loader, and we load our data batch by batch to our model. So the first two steps will be on hard disk. We have the original data set in the format of waveforms, and then we extract the spectrogram from the waveform, and we save it on the hard disk, and then we use a data loader to load all this data from hard disk to memory, and then feed forward to our network. The problem is that there's not only one type of spectrograms. For example, the spectrograms I'm showing here is MEL spectrogram. At the same time, we can also extract CQTs and also MFCCs. Most of the time, we don't know which type of spectrogram is good for our model, so we need to try all of them. That means we need to save a lot of copies of our data on the hard disk, which takes a lot of time and also occupy a lot of space. Therefore, we can solve this problem by using the on-the-fly processing. Instead of processing the data, we load the waveform first, and then we convert the waveform into spectrogram on the fly. So it happens on the memory. The problem for this approach is that if we have a really slow waveform to spectrogram conversion, then this step will become the bottleneck of the whole pipeline. The traditional audio processing tools such as Librosa, they're based on CPU. So if we apply Librosa in this step, then it would be really slow. That's why we need a fast audio processing tool that can process a batch of audio simultaneous to a batch of spectrogram at the same time. That's why we need on-the-fly processing and also GPU-based audio processing. There are some existing GPU processing tools, for example, Torch STFT, Torch Audio, Torch STFT again. The problem is that some of them are not trainable. Even some of them, although some of them are differentiable. And you can see the functionality provided by existing audio processing tools are very limited. For example, for Torch.stft, they don't have MEL spectrogram, they don't have MFCC. For Torch Audio, they don't have CQT. For TensorFlow, they have a little bit more on the functionality. For example, they have MFCC. But the problem is that you can see they are still not trainable and they still don't support CQT. The only library that supports CQT is Librosa. But for Librosa, the problem is that they don't have GPU support. You can only run Librosa on CPU, but you cannot run it on GPU. That's why I want to make a library that can process audio on GPU, then it will become very convenient for my research. So in my talk, there will be two parts. The first part, I will talk about some basics of audio processing. And after knowing the basics, I will talk about how I implement it on neural network. Because I implement all the audio processing using PyTorch, therefore we need to know what is the algorithm behind it before we can initialize the weight for the neural network to do the same thing. After that, I will talk about the applications. Let's begin with discrete Fourier transform, or DFT. The equation of DFT is shown here. If we apply Euler formula, we can break it down into real part and also imaginary part. You can see it consists of the format of an input and also a kernel. Same for the imaginary part. If we plot it out, for example, we have an input signal like this, and the kernel will be cosine of the format like this, and k here represent the frequency of the cosine kernel. For example, k equal to 1, that means there's only one cycle of cosine here. For DFT, it basically just do the dot product between the input signal and also the cosine kernel. And we multiply it point by point. If the frequency of this kernel matches with the original signal, then we can get a high response. But since you can see the input signal has a higher frequency than the kernel, and we are using k equal to 1, and that means there's no matching signal here. So we get a really low response on this spectrum. After this kernel, we try to use k equal to 2, k equal to 3, and we try all types of k, the number of k. And if the number of k generate a kernel that has the same frequency with the input, then we can get a high response, something like this. This is how DFT works. The problem is, if we just do DFT, we lose all the time information because we apply DFT on the whole signal. Now we know the frequency component. Originally, the x-axis here is time, but after doing DFT, the x-axis here means frequency. We lost all the time information, and this is not what we want. Most of the time, we want to know at what time, what frequency is there. That's why we need to have another version of Fourier transform. We call it short-time Fourier transform. Instead of applying the kernel to the whole signal, we apply the kernel to one section of the signal. And then we slide the kernel over the whole signal, and we obtain multiple spectrums. After having multiple spectrums, we concatenate them together. So one spectrum represents one column of this spectrogram. By concatenate multiple spectrum here, different spectrum represent different time of the input signal, then we can know the frequency component of the input signal over time. And this is how short-time Fourier transform works. And if we compare the equation for short-time Fourier transform and also the equation for 1D convolutional network, we can see some similarity here. Let's take a look at the 1D convolutional neural network. It consists of input and kernel. And for STFT, you can see the format are the same. We have an input X and also a kernel cosine. The only difference is that we have two components. The first component is the real part. The second component is the imaginary part. That means we can break down STFT into two 1D convolutional network. So we initialize the first 1D convolutional network as the kernel of cosine here. And we initialize another 1D convolutional network kernels as the sine kernel here. After doing the two convolution, we calculate the magnitude, because most of the time we want to know the magnitude of the signal. Then we apply this formula and we get the final spectrogram here. For MEL spectrogram, things are quite similar, but they apply one more filter to the STFT output. They call it MEL filter banks. So the original idea of MEL filter banks is it try to imitate human hearings. So for each of the MEL filter banks, it sums up different STFT frequency bins. For example, here it sums up, for example, 100 frequency bins from the STFT result and summarize it into one single MEL bin. And if we plot out the whole process, it would be something like this. We have the STFT as the first step. Just like what I previously mentioned, after we have the STFT output, we apply the MEL kernels to the STFT output. After that, we get the MEL spectrogram here. And in this case, we have two sets of kernel. The first set of kernel is the sine and cosine kernels, and the second set of kernel is the MEL filter banks. So if we implement it into the neural network, then we have two sets of parameter that is trainable or differentiable. For MFCC, it is just one extension to the MEL spectrogram. So after getting the MEL spectrogram, we apply the discrete cosine transform along the frequency axis. Then we get the MFCC output. For MFCC, I don't have time to make the kernel trainable because I am using existing GPU discrete cosine transform algorithm from the internet. So you can just get the MFCC, but the parameter is not yet trainable. Now it comes to CQT. For CQT, the original design is to make it adapt to problem related to music, because the idea behind CQT is music related. So let's take a look at the formula of CQT and compare it to the original DFT. We can see the formula are very similar. They consist of input and also a kernel, input and kernel. The only differences are here. Originally in DFT, we have this variable k, but in CQT, instead of a variable k, they replace it by a constant q. And the q, the value of q is calculated by this formula. B means number of bins per octave. Another difference is the window length for each of the kernel. In the original DFT, there is a fixed window length n. But for CQT, the window length is a variable, and the window length is calculated by this equation. It is difficult to observe what's going on from just the equation, so let's plot it out. Now we plot out the kernel for DFT and CQT. We assume q equal to 1, and then the meaning of q is actually the number of cycles in that kernel. So if q equal to 1, that means we have only one cycle in the kernel. This is the DFT kernel and CQT kernel for frequency equal to 1 Hz. For frequency equal to 10 Hz for DFT, the kernel is like this. But since for CQT, the q is a constant, which is 1. In order to maintain only one cycle, we shorten the window so that we accommodate exactly one cycle as the kernel. The same goes for lower frequency kernels. So for DFT, the window length is fixed, but for CQT, the window length is variable in order to accommodate exactly one cycle. Then you can see one problem here. For CQT, if we start with a really low frequency kernel, then we have a really long kernel. And this really long kernel occupies a lot of memory. For example, if our sampling rate is 44,000, then the lowest CQT kernel has 440,000 samples. And if we initialize it into the neural network, for DFT, we have a neural network kernel of the shape 4 times 44,000. But for CQT, we have the kernel of the shape 4 times 440,000. That's why in 1992, some people proposed using sparse matrix to store the CQT kernel, because we don't have that much memory to store everything. So the idea behind it is that they obtain the frequency so they convert the time domain signal into the frequency domain signal, and they also convert the time domain kernel into frequency domain kernel. If we plug in the CQT formulation here, it will become something like this. X to capital X is just STFT, and the CQT kernel to the time domain CUT kernel to the frequency domain CUT kernel is just FFT. So this is the plot of the original time domain CUT kernel, and this is the plot for the frequency domain CUT kernel. You can see that after we convert the time domain kernel into frequency domain kernel, the information is sparse. So we can use the sparse matrix to store the information so that we don't waste memory to store everything. And this is how it works when we try to implement it in neural network. Same as before, it all starts with STFD. And then after getting the input signal in the frequency domain, then we multiply it with the frequency domain CUT kernel, and then we get the output. And since the output consists of real and imaginary, we just calculate the magnitude to obtain the magnitude CUT. But there's still some problem. For example, in this algorithm, it consists of two sets of kernels. The first set of kernel is already gigantic, and the second set of kernel depends on the first set of kernel, because the second dimension of the CUT kernel must match with the first dimension of the DFT kernel. So in total, there are 2 billion parameters here, which is too huge for a neural network. That's why in 2010, another research group proposed a better idea. Instead of using the full CUT kernels, they use only the top octave CUT kernel. For example, if our number of bins per octave is 24, then we only use 24 CUT kernels here. The advantage of doing this is that we avoid a really low frequency kernel, because I've mentioned before, the lower the frequency, the longer the kernel is. So we only take the top octave kernels to avoid this problem. In this case, we reduce the tensor size a lot. So originally, in 1992, the implementation has 2 billion parameters. Now we reduce it to only 100,000 parameters. But later, I realized that because modern computer has more memory, so there's no need to use sparse matrix to store the information. Instead of converting all the kernels to frequency domain, we can just apply the time domain CUT kernel to the time domain signal. You can see this implementation is much more simpler than the previous implementation. And it also saves a lot of memories and reduce the number of parameters. For example, for the original idea in 1992, it has more than 2 billion parameters, but in this new implementation, it has only 11 billion parameters. The same goes for the 2010 CUT algorithm. We can just remove the frequency domain kernels and use directly the time domain kernels. And we successfully reduce the number of parameters. And so how fast is nnAudio compared with existing libraries like Librosa and other libraries like Kepler and Torch Audio? We conduct one experiment. In this experiment, we use 1,700 wave files from MAPS dataset, and we trim it down into 80,000 samples, which is around 1.8 seconds. And we want to know what is the time required to finish converting these 1,700 audios into spectrogram. So we conduct this test on 3 different machines. Machine A is a normal desktop, Windows desktop. It has CPU, i7 CPU, and also GTX 1070 GPU. And machine B is also a desktop, it's a Linux desktop, and it uses AMD GPU and RTX 2080 GPU. For machine C, it's a DGX station. And the result for the speed test is like this. Let's take a look at the first row. For the first row, we compare the speed for Librosa and nnAudio. You can see that no matter what machine we are testing on, nnAudio running on CPU is mostly faster than Librosa, except this case. And it is very clear that nnAudio running on GPU is much faster than Librosa on CPU and also nnAudio on CPU. So GPU is does improve the processing speed a lot. The second row here, we compare different types of COT algorithm, because previously I mentioned that there are different types of COT implementation, and we want to know which COT implementation is faster. And you can see 2010, the original version is not as fast as the COT10 version 2. For version 2, I removed the frequency domain kernels. That's why we can make it faster. And for 1992 version 2 is, if you're using GPU, is faster than CQT 2010. So the conclusion here is that CQT 1992 version 2 is actually the best if you run it on GPU. And for last row here, we compare our library to some existing GPU processing library like Caprit and also Torch Audio. For Windows 10, because Torch Audio doesn't support Windows operating system, so we don't have any result for machine A. But if we compare Caprit to nnAudio, you can see that nnAudio is much faster than Caprit. For Caprit, they don't have CQT, that's why we don't have comparison here. The same goes for machine B. nnAudio is still the fastest one, and the same goes for machine C. When you use nnAudio, doing the audio processing on GPU, there's one thing you need to remember is that it takes time to initialize all the kernels. For example, for STFT, there are sine kernel and also cosine kernel. So it takes around 5 seconds to initialize these kernels. And for some algorithm, they have second set of kernel, for example, MEL spectrogram. It also takes time to initialize these kernels. But actually, the time is negligible. You can consider it as a model initialization time, except COT 1992. That's why previously I mentioned that COT 1992 is not practical. But if we improve it to COT 1992 version 2, it's actually practical again. And this is the output for my nnAudio. I compare the output to LibRosa. I make everything as similar to LibRosa as possible. Most of the output are similar to LibRosa, except CQT, because they are using the downsampling method. Each time they downsample the audio, it introduced some aliasing problem. But for me, I didn't use any downsampling, so my output is smooth. The same goes for other signal. So you can see most of the signal spectrogram output are same as LibRosa. And let's have a look at some demonstration. Okay, let me now demonstrate how to use nnAudio. So for example, we have a data loader, and this data loader loads the data set called MusicNet. Okay, let's wait a second. It's loading the data. And let's listen to some of the audio samples. Because I'm casting all the tensor to GPU, so it takes some time. Okay. And the second audio, the third audio.
You can actually not hear the audios.
Sorry?
I can't hear the audios.
Oh, you cannot hear the audios. Oh, okay.
It's okay, I think.
Oh, okay. Okay. Yeah, maybe you guys cannot hear the audio. So my point is that this data loader loads a batch of audio. In this case, I load 16 audios at the same time. So it's a tensor of shape 16 and then the length of the audio. So when using nnAudio, we can process a batch of audios into spectrogram. So this line is initialization for the STFT algorithm. It's just like neural network. After you initialize the layer, then you just flip forward that batch of audio to this layer, and then you get the batch of spectrograms, and we can visualize the whole batch. So the same goes for MEL spectrogram. You initialize the MEL spectrogram layer and you feed forward the audio, you get the MEL spectrogram result. It depends on what spectrogram you want to use, then you just change the layer. And in the end, we also have MFCC. And yes, this is how we use nnAudio. It's just like a neural network. You just initialize the layer and feed forward the audio you want to convert, and you get the spectrograms already. So we can do it into model training. Every time we load a batch of audio, we directly convert it to a spectrogram on the fly without any pre-processing. Okay, then let's go back to our slides. Let's talk about one application. Because I'm working on music transcription, that's why my application is related to music transcription. For example, we have a data set, MusicNet, and it consists of 330 audio recordings. And the experimental setup is that because the recordings are waveform, and we don't know which spectrogram is best for the model, so we try out 4 different types of spectrograms. The first one is linear spectrogram, another one is log frequency scale spectrogram, and MEL spectrogram and CQT. So the traditional way to do it is we process all the audio into spectrograms and save it on the hard disk. But if we use nnAudio, we just process everything on the fly. And we also want to explore different parameters for the spectrogram. For example, for STFT, we have the NFFT parameter. So the whole workflow is that the data loader will chop the audio from the original recording, and once we get that segment of audio, we use nnAudio to convert it to a spectrogram on the fly. And then, for example, we use a very simple linear layer to classify what pitch is being played in this frame. Then we can just use one layer like this. And then we get the output and we apply threshold, and we can see what note is being activated. And we apply the loss between this output and also the original label, either by MSC loss or BCE loss. So when using nnAudio, because you don't need to do any pre-processing, what you need to do is just to change this layer. So we can easily explore different types of spectrograms and also different parameters to see which spectrogram gives you the best result. The dashed line here represent the original MusicNet paper. They get a performance something around here. And for the blue dots, it represents CQT. So you can see for CQT, the number of bins, if we increase it. So for CQT, there's 2 parameters affecting the number of bins. The first one is number of bins per octave. Another one is the number of bins. So if we increase the number of bins per octave, you can see it does increase the performance a little bit. But if we further increase it, the performance starts deteriorated. For other spectrogram types like log spectrogram, you can see if we have a really low number of bins, then the performance is really worse. But if we keep increasing the number of bins, we are increasing the resolution to the time axis, to the frequency axis. That's why we get a better transcription result. And we can also explore other parameters like the segment length. But according to my experiment, the segment length doesn't affect that much. Another feature for nnAudio is the trainable kernels. That means that you can also do the gradient descent on the DFT kernel, CQT kernel. So original DFT kernel might be like this. After training and doing gradient descent, you get a better kernel adapt to your problem. So let's have a conclusion here. So nnAudio allows a fast on-the-fly audio signal processing, and also nnAudio outperform existing GPU processing libraries in terms of speed. And nnAudio can also apply to various audio-related tasks like music transcription and also speech, because we now support MFCC. So you can also try it on some speech-related tasks. And in the end, so this is the GitHub to my nnAudio. If you're interested, you can scan it and play around with it. And that's the end of my talk. Thank you.
Thank you very much, Raven. It was very interesting. Do we have any questions from the audience? No, you can write them in the chat, or you can just turn on your audio. Okay, I think David asked me something during the talk. Do you think that this could run on cell phones, Raven?
I don't have any experience on developing on cell phones, so I'm also not sure. Mm-hmm. So do they support PyTorch on cell phone? I think as long as PyTorch, if cell phone support PyTorch, then you can run nnAudio, because nnAudio depends on PyTorch. As long as you can run PyTorch, then you can run nnAudio.
Yeah, I think it might be possible. Yeah. For the rest, so if people want to get started with nnAudio, they should visit your GitHub page. There's some nice tutorials on that where you can start building a neural network or just do the spectrogram extraction. Okay, I was just reading if there's any other questions. Not really. So we'll have another talk next week, most likely on music generation, but I'll use the Google group to keep everybody up to date and send the Zoom link. So if you haven't subscribed yet, you can do that there. I'll post the link again for you. I will also send out some information about Raven's talk, the paper where you can read up on the background, and a link to his GitHub again. Thanks all for joining. If there's any other questions, do just ask on the chat. I'll leave it open for a little bit so we can discuss there. Okay. Thanks, everyone.
Thank you. I will stay here for a while, so if you have questions, you can ask me or send a message through the chat. Gao Ray asks if the kernel is trainable, how much will it change? So I only tried on some very simple problems, like the input is just a pure sine wave, and I try to classify the frequency of that sine wave. So the change is not that much. You can still see the overall shape, but they introduce some higher frequency information to the kernel. So in the final spectrogram, you get a richer information, because if you have a sine wave in time domain and you convert it to a spectrogram, it's only one single line. But somehow the neural network learned to extract more information from that single line, and they successfully classify the frequency for that sine wave more accurately. So the original COT is like this if you apply it on a pure sine wave. After training, the COT becomes something like this. I don't know if I have answered your question or not.
I think so, because he says thanks.
Oh, okay, I didn't see that.
Oh, he says he thinks it doesn't change much.
Yeah, it doesn't change much. The overall kernel is still there. Wait. Okay, for the case of CQT, if you plot out the kernel, when you look at the kernel, it's actually changed a lot. But if you look at the spectrogram, you can see the original signal is there. The only difference is that they have other signal in other frequency bin. Because in the original CQT, it's really clean. The signal concentrate on only one single bin. And after learning a new kernel, you can see there's more information in other bins.
Okay, interesting. And the effect on the resulting task is actually significant, right?
Yes, but this task is only frequency prediction. So the input is a sine wave, and we predict the frequency of that sine wave. So I'm still thinking about any other more meaningful classification task we can try on. Because I tried on music transcription. I think music transcription is too complicated for the trainable COT or trainable spectrogram. The gradient keep exploding if I apply it on polyphonic music transcription.
Mm-hmm. There might be any a simpler audio classification task, like for instance in the Mirex competition or something.
Yeah, I will look into that. Okay, for the comparison, just a second, it's the result. So the result is like this. I tried on two very simple models. One is just a fully connected layer, another one is CNN. The blue line here means a trainable kernel, and the orange line means non-trainable kernel. And this is the loss for the task. So you can see if we make the kernel trainable, the loss is smaller than the non-trainable kernel. The same goes for other spectrogram type. This one is for STFT. Well, spectrogram. You can see that the blue one, the trainable one, is always smaller loss than the non-trainable one. The minimal frame size, I think usually it depends on your sampling weight. If your sampling weight is 16,000, usually people use 512. Oh, sorry, is it? Yeah, 512 as the frame size. And I think you can even use 2 or 4. But the problem is if you use such a small frame size, does it produce you any meaningful result? I haven't tried that small yet. So the smallest I try is 512.